All right, everybody. I apparently didn't realize that Avogadro's law and the ideal gas law were cut off from the other video, so I apologize. So I'm just going to quick go over what Avogadro's law is and what the ideal gas law is and some examples of problems that we can do. So Avogadro's law is simply that at a constant pressure and temperature, the volume is directly proportional to the number of moles of gas. This goes along with Charles' law and Boyle's law that we already covered. So if you can read in the screen and you can maximize it, volume is directly proportional to the number of moles in a substance, because when an amount of gas increases at constant temperature and pressure, the volume is going to increase as well, because the greater the amount of gas particles will take up more space. Think of expansion. So the formula that we use is V1 over N1 equals V2 over N2. And that little sideways fish is the proportionality sign. So here's our image of Avogadro's law. Each of these balloons for nitrogen, hydrogen, argon, and methane hold 1 liter of gas at 25 degrees Celsius and 1 atmosphere. So that's constant temperature and pressure. And each balloon contains 0.041 moles of gas, or 2.5 times 10 to the 22 molecules. So looking at it from the viewpoint of Avogadro's law, if we increase the volume, if we increase the amount of particles, we're going to increase the volume of the container, or that the space the moles take up. Okay, so here's a practice problem. Suppose we have a 12.2 liter sample containing 0.5 moles of oxygen gas at a pressure of 1 atmosphere and a temperature of 25 degrees Celsius. If all of this oxygen was converted to ozone at the same temperature and pressure, what would be the volume of the ozone? Okay. So where are we going? We want to know the volume of ozone. Okay. However, we have the initial volume of oxygen and we have the number of moles of oxygen. We don't have the number of moles of the ozone or the volume of the ozone. Okay. We know that that's the information that we need. We also need a balanced equation showing how O2 becomes ozone. So the first thing we need to find out is how many moles of ozone are produced by 0.5 moles of oxygen. So there's our equation. 3 moles of oxygen as a gas produces 2 moles of ozone, also as a gas. So we know with our stoichiometry, if we have 0.5 moles of O2, we need to find out how many moles of O3 we have, and it's a 2 to 3 ratio. So 2 moles of O3 over 3 moles of O2. So we find out that we actually have 0.33 moles of ozone. Now, do we have enough to solve? Yes, we do. So if we use our V1 over N1 equals V2 over N2, and we substitute in our quantities and solve for V2, V2 is going to equal V1 times N2 over N1. And we plug it in and we find that we get 8.1 liters. Now, this problem was a little extra. Typically, a problem would just have, the volume in moles, much like the Boyle's and Charles' law problems that I gave you. That's all there is to it for Avogadro's law. Okay. All right. So now let's go ahead to the ideal gas law. So for the ideal gas law, we are using all of the other laws that we've already practiced. Boyle's law, Charles's law, and Avogadro's law, and the combined gas law. If we replace the proportional sign with the equal sign and a proportionality constant known as R, which is also known as the universal gas constant, we are able to solve for any of the variables given 3 of the other ones. We can also rearrange the equation to give us PV equals nRT, which is known as the ideal gas law. Make sure you pay attention to what the value of R is, because there's several different forms of R. It depends on the units of R that for which one you're going to use. For our example, we're using liters, atmospheres, Kelvin, and moles, meaning that our volume has to be in liters, our pressure has to be in atmospheres, our temperature has to be in Kelvin, and we're using units of moles. Okay, this is an equation of state for a gas where the state of the gas is its condition at a given time. Any gas of the basis law is said to be behaving ideally, which is really a hypothetical situation, and it's a hypothetical substance because honestly there's no ideal situations. So why would you use this? Well, ideal gas law can be applied to any problem. Place the variables that change on one side of the equal sign and the constants on the other. So here we go. Suppose we have a sample of ammonia gas with a volume of 7 milliliters. So we're going to convert that to liters. So 7 milliliters equals 0.007 liters. A pressure of 1.68 atmospheres. And the gas is compressed to a volume of 2.7 milliliters at a constant temperature. So our temperature is constant. So we have a V1 and a V2. And they want us to use the ideal gas law to calculate the final pressure. So just looking at this equation, we know that we have a V1 and a V2, temperature is constant, and we need a pressure, right? So let's figure out how we're going to do this using all of our gas laws. That's everything I already wrote down. We know that the variables that are changing are pressure and volume. The pressures that remain constant are the moles, the universal gas constant, and the temperature. Write the ideal gas law, collecting the change variables on one side and the variables that do not change on the other. PV equals nRT. This leads us to Boyle's law. P1 V1 equals P2 V2. All this example problem is showing you is how all of the other gas laws are really derived from the ideal gas law if you know who's changing and who's staying constant. And this is the answer. So if we plug in all of our values and solve for P2, so it's P1 times V1 divided by V2, that's going to give you a value of P2. And as you see on the slide, that gives you a value of 4.4 atmospheres. And that's how they use the ideal gas law to solve. Okay. Now you can check your answer, make sure it's reasonable by knowing that as if the volume decreased, then the pressure should increase, and it does if you look at your final numbers. I will go over this problem with you now. Sorry, I jumped ahead accidentally. So a sample of diborane gas, a substance that bursts into flame when exposed to air, yay, has a pressure of 345 torr at a temperature of negative 15 degrees Celsius and a volume of 3.48 liters. The red does not like to come off of the board, apparently. Okay. So So what do we have? We have a pressure of 345 torr, which we're going to have to convert into atmospheres. So we're going to have to divide it by 760 because that's the conversion factor. We have a temperature of negative 15 degrees Celsius, and we have to convert it into Kelvin. And we have a volume of 3.48 liters. That's actually okay. And we know that our formula is B2H6. I'm just going to write it down just in case. If the conditions are changed, that the temperature is 36 degrees Celsius, so these are all of our initial. So now we're changing our temperature and we're changing our pressure. So this is 2, 2, 2. We have our P2 is 468 torr, and we're going to divide it by 760 to convert it to atmospheres. We have our temperature of 36 degrees Celsius. Add 273 to convert to Kelvin. Since it's a change, we don't really need to, but I've kind of already started. And we're looking for what V2 is. This looks like we're setting it up for the combined gas law. Let's see where the book is going. Not that way. Okay. So those are our temperatures. So we have 258 K. And we have 309 K. We have our volume. And we have our pressures. They want us to use the ideal gas law, but I think we all know it's going to turn into the combined gas law. And as you plug in everything, our volume is 3.07 liters. Once you plug in your T2, your P1, your V1, your T1, and your P2. Okay. All right. So I'm going to actually take a break from the textbook problems, and I'm going to give you a very basic ideal gas law problem from another textbook or experience. Okay. So we need to calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 Kelvin. And what is the volume? Using the ideal gas law. PV equals nRT. V is going to be equal to nRT over P. Plug and chug. 0.845 moles times our universal gas constant, which is 0.08206, times our temperature. I'm going to actually just expand this. Okay. So I'm going to actually go back and now you have that. V is going to be equal to N45 times R, 0.08206, times T, which is 315 Kelvin. I'm not writing the units to conserve space. 1.37 would be your pressure. Work this all out, and you should get 15.9 liters as your answer. 15, that's not a 16, that's a 15. Okay, let's try another one. Okay, so if we have an 8.5 liter tire, so our volume is 8.50 liters. I know that liters is the unit for volume. That's how I can identify that. We have our number of moles is given as 0.552 moles. And we have a temperature of 305 Kelvin. What is the pressure of the gas in the tire? All right, so let me read the problem again to you so that way you can pause it if you need to. An 8.5 liter tire contains 0.552 moles of gas at a temperature of 305 Kelvin. What is the pressure in atmospheres of the gas in the tire? Well, PV equals nRT. We're going to solve for pressure. So our equation is pressure equals nRT over V. Plug and chug. So we have 0.552 times 0.08206 times 305 all over 8.5. The pressure in the tire is going to be 0.552 times 0.08206 times 305 divided by 8.5, 1.63 atmospheres. Great. Okay, that concludes gas laws.